Now that we have added multiplication in the form of the dot product for vectors and its generalization, the matrix product for matrices, let's establish the algebra of these operations. So let's look at addition and scalar multiplication in a little more detail. We have already considered the algebra of addition and scalar multiplication, both for vectors and matrices. So as a reminder of the algebra that we have established so far, is whether or not A, B, C here are matrices or whether they're vectors with associated scalars alpha and beta, we know that addition works the way scalar addition does, namely it's commutative, it's associative, so we don't need parentheses when we write A plus B plus C, that we have a zero, so A plus 0 is equal to A, that there is an additive inverse, so given an A, there is some element, A plus A tilde, that gives us 0 again, so it cancels out, and that scalar multiplication distributes over addition. So alpha times A plus B is alpha A plus alpha B, and as a consequence, if we say that scalar multiplication binds more tightly than addition, that we do it first, it means that we don't need the parentheses on the right-hand side, that alpha plus beta, if we add the scalars first and multiply it into A, or if we multiply the scalars into each of the matrices and then add the corresponding matrices, the result is the same, and similarly for multiplication. A couple of rules that are missing that we get out of the rules that we've just written down is that the zero element is unique, and for matrices it looks like a matrix of whatever size with all entries equal to 0. The scalar product, so 0 times A, the 0 on the left here is a scalar 0, the 0 on the right is the matrix 0, so 0 times the matrix A is equal to the 0 matrix, and the uniqueness of the additive inverse, there is only one such, and we get it by taking A and multiplying A by the scalar minus 1. So we actually have three scalars that are important here. 1 times A is equal to A, 0 times A is equal to the 0 matrix, and minus 1 times A is the additive inverse. So A plus minus 1 times A is equal to the 0 matrix. We then define the product of two matrices, and let's look at that in a little bit more detail. Here's a matrix A and a matrix B, and if you try and multiply A times B, well, A has 3 entries in each row, B has 3 entries in each column, so that's possible. A times B works out to this matrix over here. The size is the inner indices of A and B will add up, and it's the outer indices, the number of rows in A times the number of columns in B, that determine the size of the product. If I try and multiply B times A, I see that that doesn't even exist because of a size mismatch. So B is size 3 by 3, A is size 2 by 3, and as a consequence, the inner indices here differ. B has 3 entries in each row, and A has 2 entries in each column, and therefore those dot products do not exist. So AB exists, but BA does not exist if there's a size mismatch. Now, even when the sizes are consistent, BA may exist and AB may exist, but to make that possible, A has to be size m by n, and B has to be size n by m. And if I look at the sizes of A times B and B times A, I see that A times B has size m by m, and B times A has size n by n. So if m and n are not the same, then AB and BA are matrices of different sizes. Now, when m equals n, then the sizes are the same, but still A times B is not equal to B times A in general. So here's an example that matrix A with entries 1, 1, 2, minus 1, and B with entries 1, 3, and minus 2, 4. And if you compute AB, you get minus 1, 7, 4, 2, and BA gives you 7, minus 2, 6, minus 6. So AB is not equal to BA in general, even if both of the products exist and are the same size. However, it's not necessarily the case. Look at this example here. A is 2, 3, and 2, 3. B has entries 1, 3, and 2, 2. And if you multiply out AB and BA, you get the same result. So AB is different from BA in general, but there are special cases where the products are actually the same. Now, when A is a square matrix, we can multiply A by itself. So we can define the power of a matrix, of a square matrix A, as simply A to the K is equal to A times A times A, K factors A in this product. So if A is equal to -1, 2, -3, 4, for example, we can compute A cubed as A times A times A with this particular result on the right-hand side. There are matrices with special patterns to the entries that will turn out to be of interest, and let me show you a few of these. So one of them we've already seen, it's the zero matrix, the matrix that has all zeros. If you look at this example here, the zeros in both cases are matrices. The zero matrix times A is equal to a zero matrix, A times a zero matrix is equal to the zero matrix. And all that's required is that that symbol zero, that matrix, actually have a size that is consistent for this product to exist. So the zero matrix times A, where the zero matrix is 3 by 2, times an A that's 2 by, in this case, 2 by 4, is a 3 by 4 zero matrix. So the zeros on either side here have to have consistent sizes, but those sizes need not be the same. Similarly here, A times a zero matrix is equal to the zero matrix. Another example of a matrix that's of interest is the identity matrix. It looks like this. It's all zeros except the entries on the main diagonal. So the entry 1, 1, 2, 2, all the way through n is equal to 1. Everything else is 0. It has the property that when we multiply that into a matrix A, it doesn't change the matrix A. So I times A is equal to A, and A times I is equal to A. And again, I'm assuming here that the i's are of consistent sizes. A remark that's in order here is if I take the scalar product alpha times A, I can also write that as a matrix product. I can simply write A as A times I and push the alpha into the I. So 3 times the matrix A is equal to that matrix A times I with the 3 multiplied ends. When you multiply that out, you get the same result on both sides. Another thing to notice is that we can use a submatrix of I to extract rows and columns from a matrix. So as my first example here, let's take a matrix A and use the first and the third row of an I and multiply that in from the left. And what this says is 1 times the first row plus 0 times the second row plus 0 times the third row of A. So we get the first row of A copied in. And the second row here is 0, 0, 1. It copies in the third row of A. It's probably easier to see if we write it in our computational layout, where we have that the first row of the result is equal to the first row of the matrix A. The second row of the result is equal to the third row of the matrix A. We can do something similar with columns, but this time around we have to multiply from the other side. So here's my matrix A, and I'm multiplying with some columns of a matrix I to get my result. And if you look at the computational layout, what you see is the first column of the matrix A plus 0 times the second column plus 0 times the third column copies in the first column of the matrix A. Similarly, 0, 0, 1 copies in the third column of the matrix A. Another consequence of that is we can also use a matrix I with some rows interchanged or columns interchanged equivalently to permute the rows of a matrix or the columns of a matrix. So here's an example where I've interchanged rows 1 and 3 of the I matrix, and I multiply that into a matrix A from the left. And what this does, well, easier to see in the layout, 0 times the first row plus 0 times the second row plus 1 times the third row simply says copy in the third row. Here it's copy in the second row and copy in the first row. So it interchanges the rows of the matrix A according to this pattern of the matrix on the left. We can also interchange columns in the same way. So this time around I have to multiply my permutation matrix that I with the columns interchanged from the right. And in the layout, it's easy to see. I've got my matrix A. The first column of the result is 0 times the first column plus 0 times the second column plus 1 times the third column of A. So the third column of A, second column of A, and first column of A. Now let's look at the properties of the matrix multiplication. The theorem that we can establish is that A times B times C, that as long as we keep the order consistent, since A times B is not equal to B times A, and as long as we assume that that product actually exists, then the order in which we group the terms doesn't matter. So if we compute A times B first and then multiply in C, or if we compute B times C first and then multiply in A, we get the same result as long as we keep the order of the matrices the same. Now, similarly, A, that multiplication will distribute over the addition. So A times B plus C is equal to AB plus AC. And again, A is on the left and therefore has to stay on the left as we multiply this out. Since we can't commute, we have to establish the same property when A is on the other side of that addition. So B plus C times A is equal to BA plus CA. And again, the A this time is on the right and stays on the right as we multiply this out. Scalar multiplication works similarly. Alpha times the product AB is equal to alpha times A, multiply that out first, times B, or A times multiply the alpha into the B, and then multiply the products. We also had the operation transpose, so we need to add that into our set of rules into our algebra. And what we have is if we take a matrix A and transpose it, so A transpose, and transpose that result, well, we get A again. So make a row into a column, and then make that column back into a row, we get the same matrix as before. The transpose of a sum, we can see it as the transpose of A plus the transpose of B, so that transpose simply acts on both of these matrices individually. And if we establish the convention that transposes happen before addition, then we can dispense with the parentheses in this expression and simply write A transpose plus B transpose. We next have alpha times A, a scalar times A, quantity transpose, that we can simply scale the transpose of the matrix A. The last property here is a little bit more surprising, that A times B quantity transposed is equal to, well, the matrices A and B get transposed, but their order changes as well. The order gets interchanged, B transpose, A transpose. Let me explain that one in a little bit more detail. If I look at the product AB, the definition was that we listed the A vectors as rows, the B vectors as columns, and that we wrote the dot products of the A vectors and the D vectors at the corresponding intersections. If I want to interchange the A's and the B's, well, I'll get this second expression here. I'll have to write the B vectors as rows and the A vectors as columns. But originally I had the B vectors as columns, so I'm going to have the transpose of B on the left in this multiplication. And similarly, the A's originally were written as rows, and therefore the transpose of the matrix A to get the columns of A. Now, when I compute the dot products that results in, if I look at the form A times B, so for example here, A2, all the dot products with A2 are in the row that A2 is in. Over on the other side, the dot products with A2, all the dot products with A2 are in the column that A2 is in. So while I'm getting the same dot products as before, their arrangement is transposed compared to what I had. And therefore, the product of A times B transposed is equal to the product of B transpose times A transpose. Now, one thing that happens with all of these is that some of the scalar algebra patterns that we are used to do not hold for matrices. So the first one we've already seen, that A times B is not equal to B times A. We have to be careful of the order. We can't interchange matrices as we go. The next example is that we have not defined any kind of division. As a consequence, if we have something like A times B is equal to 0, so a product of two matrices is equal to 0. Here's an example. That does not imply that A is equal to 0 or B is equal to 0. In scalar operations, we could divide out one of these and come to that conclusion. But with matrices with no division, that's not true. And so here's the example where I've got an A that's not the 0 matrix, a B that's not the zero matrix, and yet those two matrices multiply out to the zero matrix. Even powers of a matrix, that result doesn't hold. So here's a matrix A, it's not the zero matrix. I square it, and I get the zero matrix from that result. So we can't just cancel a matrix in an expression. Similarly, if I have A times B is equal to A times C, again, in scalar multiplication, we might be tempted to cancel out the A and say that therefore B is equal to C. With matrices, again, that doesn't hold, since we can't cancel. The best we can do is simply put both of these multiplications on the same side and factor out an A, and so AB is equal to AC becomes A times the matrix B minus C is equal to 0. So that's the product of two matrices equal to 0. We've just rewritten our condition a little bit, but that's the best that we can do. The other thing is patterns that we've learned for speed. So for example, here's a multiplication pattern, A plus B times A plus B. When we multiply that out carefully, we get A squared plus A times B plus B times A plus B squared. Well, in scalar multiplication, AB and BA are the same and therefore add up to 2 times AB. In matrix multiplication, we can't interchange the order, so we have to keep both of these entries in our result. Something similar happens with A plus B times A minus B, where we get A squared minus AB plus BA minus B squared, and AB and BA do not cancel. If we look at the dot product compared to matrix multiplication, right, the dot product is just a special case. So if we assume U, V, and W are vectors now of consistent sizes, well, we have U dot V is equal to V dot U. The dot product is commutative. We can interchange the order of U and V. Similarly, the dot product distributes over addition. Scalar multiplication distributes over the dot product. So the algebra is much closer to the algebra of scalar equations. And I'd just like to show you why U dot V is equal to V dot U, why that simplifies. If I look at my matrix product that I had before, A times B transpose is equal to B transpose A transpose, if I take A to be a row vector, if U and V are column vectors, A would be U transpose, and B a column vector. Then A times B is just U transpose V, and U transpose V is the dot product of U and V. So when I plug that into that formula of that AB quantity transpose is equal to B transpose A transpose, what I get is that U transpose V quantity transpose turns out to be the transpose of the individual vectors with the order interchange, so V transpose U, and V transpose U is V dot U. So what we've written down is that U dot V is equal to V dot U. One consequence of that is the algebraic patterns that we are used to from scalars, they will hold. U minus V dot with U plus V multiplies out to U dot V minus V dot V, so U dot V and V dot U will cancel. But we still do not have division. So U dot V is equal to U dot W. We can simply rewrite that as U dot V minus W equal to 0, but that's the best we can do. We have a dot product of two vectors equal to 0. Since U dot V equals 0 does not let us conclude that U is equal to 0 or V equals 0. So here's a counterexample. If U is the vector 1, 2, and V is the vector minus 2, 1, they're non-zero vectors. If I compute their dot product, that dot product is indeed equal to 0. Some examples now. So example number 1, let's look at the product of more than two matrices. So look at A, B, and C, and try and multiply A times B quantity times C. So here is the numerical layout. If I compute A times B first, and then multiply in C afterwards. So here's my matrix A times the matrix B, and multiply that out, we get the matrix A times B. And now that we have A times B, we can multiply in C and obtain the overall product A times B times C. We can parenthesize that differently. We can compute B times C and then multiply in A from the left instead. So here's my matrix B, here's my matrix C, multiply them together to compute the product B times C, And now that we have B times C, multiply in A from the left to compute A times B times C. And if you compare the two operations here, you'll see that the final result is the same, but the intermediate results are different, of course. One question that we can ask is how many multiplications did we do to compute these two results? The parenthesization on the left, where we compute A times B first and then multiply in C, or if we take B times C first and then multiply in A. If we count the number of multiplications, we'll see that the number of multiplications we do in each case is different. And so I'd like to have you do the exercise where you simply compute how many multiplications you do for these two examples and see which one you will have to do less work for. Here is the computation in Python, a matrix A, a matrix B, a matrix C, and multiplication with NumPy is written with that at symbols, A at the product B at C, and we indeed get the result that we expect. Here's an application of matrix products. Substitution into a set of equations is actually a matrix multiplication. Look at this set of equations here, and notice that we can write this as a matrix A times a vector x is equal to B, where that vector x is just our two variables, x1 and x2, and the matrix A is the coefficients of those two variables. And if you multiply that out, you'll indeed see that A times x equals B is equivalent to this expression. Now what we want to do is we want to substitute for x1 and x2. So let's say x1 is expressed in terms of two new variables, x1 tilde and x2 tilde, and similarly for x2, so I have this expression for x1 and x2 that I could substitute into my previous set of equations. But one thing to notice is that this substitution can also be written in terms of a matrix times a vector, namely the vector x is equal to the matrix B times x tilde, where the vector x tilde is just my x tilde variables written into a vector, and B is the set of coefficients in the substitution. If I substitute directly, if I take my x1, x2 and substitute into my original problem, I get this expression here. I get 12x1 tilde minus x2 tilde equals 8, minus 5x1 tilde minus 10x2 tilde equals 5. But I can also substitute in the matrix expression. I have Ax equals B and x equals B times x tilde. And when I write that out, I get that A times B times x tilde is equal to B, and we already know that with matrix multiplication, we can group either way, and so we can group this as A times B times the vector x tilde. And when we check, indeed, that multiplication works out exactly as before. A times B is equal to the coefficients here. So let's use our Python code to actually compute it. So we have got the matrix A, the matrix B, and we compute A times B, and we indeed get the coefficients that we had with the substitution. So a substitution of variables in a set of linear equations can be written as a matrix product. So one use for a matrix product that will turn out to be quite interesting in what's to come. Our takeaway then. We have obtained the algebra of matrix addition, scalar multiplication, and matrix multiplication. And basically what we've seen is that we can do our algebra similar to scalar algebra with a few caveats. With matrices, we can't interchange the order of the matrices, so A times B, A on the left, will have to stay on the left in all of the operations that we might carry out, that there's no division, so we can't just cancel matrices, and with those two caveats, and the fact that patterns that we had learned for speed, such that A plus B quantity squared is A squared plus B squared plus 2AB, that those patterns don't hold because of the lack of commutativity. Apart from that, everything holds, and we can just do algebra the way we're used to. We've also seen some special matrices that do interesting things when we multiply them into a given matrix A. We've seen the zero matrix, the identity matrix, and permutation matrices. And we've seen the fact that we can stack matrices in a layout to perform matrix multiplication. When we combine that with partitioning in the layout, that will prove very useful.